Describe the crucial role of physics in science, technology, and society. Unit 1. Physical quantities and measurement. Conceptual linkage. This unit is built on measurement, Science 8 scientific notation, Maths IX. This unit leads to measurement, Physics XI. Physics 9-2 Unit 1, Physical quantities and measurement. Investigation skills. Science, technology and society connection. Major concepts 1.1 Introduction to Physics 1.2 Physical quantities 1.3 International system of units 1.4 Prefixes, multiples and submultiples 1.5 Scientific notation Standard form 1.6 Measuring instruments. Meter rule Vernier calipers Screw gauge Physical balance Stopwatch Measuring cylinder 1.7 An introduction to significant figures. When you can measure what you are speaking about and express it in numbers, you know something about it. When you cannot measure what you are speaking about or you cannot express it in numbers, your knowledge is of a meager and of unsatisfactory kind. Lord Kelvin. For your information, Andromeda is one of the billions of galaxies of known universe. The students will be able to compare the least count accuracy of the following measuring instruments and state their measuring range. I. Measuring tape. 2. Meter rule. 3. Vernier calipers. 4. Micrometer screw gauge. Make a paper scale of given least count e.g. 0.2 cm and 0.5 cm. Determine the area of cross-section of a solid cylinder with vernier calipers and screw gauge and evaluate which measurement is more precise. Determine an interval of time using stopwatch. Determine the mass of an object by using different types of balances and identify the most accurate balance. Determine volume of an irregular-shaped object using a measuring cylinder. List safety equipments and rules. Use appropriate safety equipments in laboratory. The students will be able to determine length, mass, time, and volume in daily life activities using various measuring instruments. List with brief description the various branches of physics. Man has always been inspired by the wonders of nature. He has always been curious to know the secrets of nature and remained in search of the truth and reality. He observes various phenomena and tries to find their answers by logical reasoning. The knowledge gained through observations and experimentations is called science. The word science is derived from the Latin word scientia, which means knowledge. Not until 18th century, various aspect of material objects were studied under a single subject, called natural philosophy. But as the knowledge increased, it was divided into two main streams: physical sciences, which deal with the study of non-living things, and biological sciences, which are concerned with the study of living things. Measurements are not confined to science. They are part of our lives. They play an important role to describe and understand the physical world. Over the centuries, man has improved the methods of measurements. In this unit, we will study some of physical quantities and a few useful measuring instruments. We will also learn the measuring techniques that enable us to measure various quantities accurately. 1.1 Introduction to Physics. In the 19th century, physical sciences were divided into 5 distinct disciplines: physics, chemistry, astronomy, geology, and meteorology. Most fundamental of these is the physics. In physics, we study matter, energy, and their interaction. The laws and principles of physics help us to understand nature. The rapid progress in science during the recent years has become possible due to the discoveries and inventions in the field of physics. The technologies are the applications of scientific principles. Most of the technologies of our modern society throughout the world are related to physics. For example, a car is made on the principles of mechanics, and a refrigerator is based on the principles of thermodynamics. In our daily life, we hardly find a device where physics is not involved. Consider pulleys that make it easy to lift heavy loads. Electricity is used not only to branches of physics. Mechanics, it is the study of motion of objects, its causes and effects. Heat, it deals with the nature of heat, modes of transfer and effects of heat. Sound, it deals with the physical aspects of sound waves, their production, properties and applications. Light, optics, it is the study of physical aspects of light, its properties, working, and use of optical instruments. Electricity and magnetism, it is the study of the charges at rest and in motion, their effects, and their relationship with magnetism. Atomic physics, it is the study of the structure and properties of atoms. Nuclear physics, it deals with the properties and behavior of nuclei and the particles within the nuclei. Plasma physics, it is the study of production, properties of the ionic state of matter, the fourth state of matter. Geophysics, it is the study of the internal structure of the earth. Physics 9.3 Unit 1, Physical Quantities and Measurement. Quick Quiz 1. Why do we study physics? 2. Name any 5 branches of physics. A. B. Figure 1.1. A. A vacuum cleaner. B. A mobile phone. Do you know? Wind turbines are used to produce pollution-free electricity. Figure 1.2. Measuring height. Get light and heat, but also mechanical energy that drives fans and electric motors, etc. Consider the means of transportation such as car and aeroplanes, domestic appliances such as air conditioners, refrigerators, vacuum cleaners, washing machines, and microwave ovens, etc. Similarly, the means of communication such as radio, TV, telephone, and computer are the result of applications of physics. These devices have made our lives much easier, faster, and more comfortable than the past. For example, think of what a mobile phone smaller than our palm can do. It allows us to contact people anywhere in the world and to get latest worldwide information. We can take and save pictures, send and receive messages of our friends. We can also receive radio transmission and can use it as a calculator as well. However, the scientific inventions have also caused harms and destruction of serious nature. One of which is the environmental pollution, and theater is the deadly weapons. 1.2 Physical quantities. All measurable quantities are called physical quantities such as length, mass, time, and temperature. A physical quantity possesses at least two characteristics in common. One is its numerical magnitude and the other is the unit in which it is measured. For example, if the length of a student is 104 centimeters, then 104 is its numerical magnitude and centimeter is the unit of measurement. Similarly, when a grocer says that each bag contains 5 kilograms sugar, he is describing its numerical magnitude as well as the unit of measurement. It would be meaningless to state 5 or kilogram only. Physical quantities are divided into base quantities and derived quantities. Physics 9 for Unit 1, Physical Quantities and Measurement. Volume, 1 centimeter 1 milliliter. 1 centimeter 10 centimeters equals 1 decimeter. Base quantities. There are 7 physical quantities which form the foundation for other physical quantities. These physical quantities are called the base quantities. These are length, mass, time, electric current, temperature, intensity of light, and the amount of a substance. Derived quantities. Those physical quantities which are expressed in terms of base quantities are called the derived quantities. These include area, volume, speed, force, work, energy, power, electric charge, electric potential, etc. 1.3 International System of Units. Measuring is not simply counting. For example, if we need milk or sugar, we must also understand how much quantity of milk or sugar we are talking about. Thus, there is a need of some standard quantities for measuring, comparing unknown quantities. Once a standard is set for a quantity, then it can be expressed in terms of that standard quantity. This standard quantity is called a unit. With the developments in the field of science and technology, the need for a commonly acceptable system of units was seriously felt all over the world, particularly to exchange scientific and technical information. The 11th General Conference on Weight and Measures held in Paris in 1960 adopted a worldwide system of measurements called International System of Units. The International System of Units is commonly referred as SI. Base units. The units that describe base quantities are called base units. Each base quantity has its SI unit. Base quantities are the quantities on the basis of which other quantities are expressed. The quantities that are expressed in terms of base quantities are called derived quantities. Volume is a derived quantity. 1L equals 1000 milliliters. 1L equals 1 decimeter. 3 equals 10 centimeters. 3 is equal to 1000 cm. 1 milliliter equals 1 centimeter. 3 express 1 m in liters. L. Physics 9.5 Unit 1, Physical Quantities and Measurement. Table 1.1 shows 7 base quantities, their SI units and their symbols. Table 1.1, Base quantities, their SI units with symbols. Derived units. The units used to measure derived quantities are called derived units. Derived units are defined in terms of base units and are obtained by multiplying or dividing one or more base units with each other. The 2-3 unit of area, meter, and the unit of volume, meter, are based on the unit of length, which is meter. Thus the unit of length is the base unit, while the unit of area and volume are derived units. Speed is defined as distance covered in unit time, therefore its unit is meter per second. In the same way, the unit of density, force, pressure, power, etc. can be derived using one or more base units. Some derived units and their symbols are given in the Table 1.2. Table 1.2, Derived quantities and their SI units with symbols. Physics 9.6 Unit 1, Physical Quantities and Measurement. 1.4 Prefixes. Some of the quantities are either very large or very small. For example, 250,000 m, 0.002 W, and 0.000002 G, etc. SI units have the advantage that their multiples and submultiples can be expressed in terms of prefixes. Prefixes are the words or letters added before SI units such as kilo, mega, giga and milli. These prefixes are given in Table 1.3. The prefixes are useful to express very large or small quantities. For example, divide 20,000 G by 1,000 to express it into kilogram, since kilo 3 represents 10 or 1,000. Quick quiz 1. How can you differentiate between base and derived quantities? 2. Identify the base quantity in the following: I, speed; 2, area; 3, force; 4, distance. 3. Identify the following as base or derived quantity: density, force, mass, speed, time, length, temperature and volume. Table 1.4 shows some multiples and submultiples of length. However, double prefixes are not used. For example, no prefix is used with kilogram since it already contains the prefix kilo. Prefixes given in Table 1.3 are used with both types base and derived units. Let us consider few more examples. -1 3 -1 -1 I 200,000 milliseconds equals 200 by 10 milliseconds equals 200 kilometers. 3 2 4,800,000 W equals 4 800 by 10 W equals 4 800 kilowatts. 6 is equal to 4.8 times 10 W equals 4.8 megawatts. 6 3 3,300,000,000 hertz equals 3 300 by 10 hertz equals 3,300 megahertz. Thus, or Table 1.3, some prefixes. Table 1.4, multiples and submultiples of length. Physics 9-7 Unit 1, Physical Quantities and Measurement. 3 is equal to 3.3 times 10 megahertz equals 3.3 gigahertz. -3, 4, 0.00002 G is equal to 0.02 times 10 G equals -620 by 10 G equals 20 UG. -6 -9, the 0.000000081 mobile is equal to 0.0081 times 10 m is equal to 8.1 times 10 m equals 8.1 nanometers. 1.5 Scientific notation. A simple but scientific way to write large or small numbers is to express them in some power of 10. The Moon is 384 million meters away from the Earth. Distance of the Moon from the Earth can also be 8 expressed as 3.84 x 10 m. This form of expressing a number is called the standard form or scientific notation. This saves writing down or interpreting large numbers of zeros. Thus, in scientific notation a number is expressed as some power of 10 multiplied by a number between 1 and 10. For example, a number 62750 can be 345 expressed as 62.75 by 10 or 6.275 by 10 or 0.6275 by 10. All these are correct. But the number that has one non-zero 4-digit before the decimal, i.e. 6.275 by 10, preferably be taken as the standard form. Similarly, the standard form of -4 0.00045s is 4.5 times 10s. 1. Name 5 prefixes most commonly used. 2. The Sun is 150 million kilometers away from the Earth. Write this, A, as an ordinary whole number. B, in scientific notation. 3. Write the numbers given below in scientific notation. -1, A, 3 billion milliseconds, B, 6400000 mobile, C, 0.0000000016 G, D, 0.0000548s. 2410 G, 2210 G, 1810 G, 1510 G, 1210 G. 910G, 610G, 310G, 010G, minus 310G, minus 610G, minus 910G, minus 1210G, minus 1510G, minus 1810G, minus 2210G, minus 2410G. Earth's atmosphere to 2,500 kilometers. Ocean. Elephant. Average human 1.0 liter of water. Grain of table salt. Typical protein molecule. Uranium atom water molecules. Tidbits mass of various objects. Physics 9-8 Unit 1, Physical Quantities and Measurement. CM 190 80 70 60 50 40 30 20 10 0. A. B. 0 1 2 3. 0 1 2 3. A meter rule is a length measuring instrument as shown in Figure 1.3. It is commonly used in the laboratories to measure length of an object or distance between 2 points. It is 1 meter long, which is equal to 100 centimeters. Each centimeter, cm, is divided into 10 small divisions called millimeter, millimeter. Thus 1 millimeter is the smallest reading that can be taken using a meter rule and is called its least count. While measuring length, or distance, I must be kept vertically above the reading point as shown in Figure 1.4, b. The reading becomes doubtful if the eye is positioned either left or right to the reading point. The measuring tape. Measuring tapes are used to measure length in meters and centimeters. Figure 1.5 shows a measuring tape used by blacksmith and carpenters. A measuring tape consists of a thin and long strip of cotton, metal or plastic, generally 10 m, 20 m, 50 m or 100 m long. Measuring tapes are marked in centimeters as well as in inches. 1.6 Measuring instruments. Measuring instruments are used to measure various physical quantities such as length, mass, time, volume, etc. Measuring instruments used in the past were not so reliable and accurate as we use today. For example, sundial, water clock and other time measuring devices used around 1300 AD were quite crude. On the other hand, digital clocks and watches used nowadays are highly reliable and accurate. Here we shall describe some measuring instruments used in physics laboratory. The meter rule. Figure 1.3, a meter rule. Figure 1.4, wrong position of the eye to note the reading. B, correct position of the eye to note the reading from a meter rule. Figure 1.5, a measuring tape. Hubble Space Telescope orbits around the Earth. It provides information about stars. For your information. Physics 9-9 Unit 1, Physical Quantities and Measurement. Working of a vernier calipers. First of all, find the error, if any, in the measuring instrument. It is called the zero error of the instrument. Knowing the zero error, necessary correction can be made to find the correct measurement. Such a correction is called zero correction of the instrument. Zero correction is the negative of zero error. Main scale, outer jaws, vernier scale. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 centimeters M. Fixed jaws 0, 5, 10. Movable jaws. Vernier calipers. The accuracy obtained in measurements using a meter rule is up to 1 mm. However, an accuracy greater than 1 mm can be obtained by using some other instruments such as a vernier calipers. A vernier calipers consists of two jaws as shown in figure 1.6. One is a fixed jaw with main scale attached to it. Main scale has centimeter and millimeter marks on it. The other jaw is a movable jaw. It has vernier scale having 10 divisions over it such that each of its division is 0.9 mm. The difference between one small division on main scale division and one vernier scale division is 0.1 mm. It is called least count, LC, of the vernier calipers. Least count of the vernier calipers can also be found as given below. Figure 1.6, a vernier calipers with jaws closed. Hence, mini exercise. Cut a strip of paper sheet. Fold it along its length. Now mark centimeters and half centimeter along its length using a ruler. Answer the following questions. 1. What is the range of your paper scale? 2. What is its least count? 3. Measure the length of a pencil using your paper scale and with a meter ruler. Which one is more accurate and why? Physics 9-10 Unit 1, Physical Quantities and Measurement. 0, 1, 2. 0, 5, 10. Movable jaws. 0, 1, 2. 0, 5, 10. Movable jaws. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 centimeters M. Fixed jaws 0, 5, 10. Note the complete divisions of main scale past the vernier scale 0 in a tabular form. Next, find the vernier scale division that is coinciding with any division on the main scale. Multiply it by least count of vernier calipers and add it in the main scale reading. This is equal to the diameter of the solid cylinder. Add zero correction, Z.C, to get correct measurement. Repeat the above procedure and record at least 3 observations with the solid cylinder displaced or rotated each time. Zero error and zero correction. To find the zero error, close the jaws of vernier calipers gently. If zero line of the vernier scale coincides with the zero of the main scale, then the zero error is 0, figure 1.7a. Zero error will exist if zero line of the vernier scale is not coinciding with the zero of main scale, figure 1.7b. Zero error will be positive if zero line of vernier scale is on the right side of the zero of the main scale, and will be negative if zero line of vernier scale is on the left side of zero of the main scale, figure 1.7c. Taking a reading on vernier calipers. Let us find the diameter of a solid cylinder using vernier calipers. Place the solid cylinder between jaws of the vernier calipers as shown in figure 1.8. Close the jaws till they press the opposite sides of the object gently. A. B. There is no zero error as zero line of vernier scale is coinciding with the zero of main scale. Zero error is 0 plus 0.07 cm as 7th line of vernier scale is coinciding with one of the main scale division. Zero error is -0.1 plus 0.08 cm as 8th line of vernier scale is coinciding with main scale. Zero error is negative as zero line of the vernier scale is on the left side of the main scale. 0, 1, 2. 0, 5, 10. Movable jaws. Figure 1.7, 0 error, A, 0, B, plus 0.07 centimeters. Copyright symbol CM-0.02. Figure 1.8, a cylinder placed between the outer jaws of vernier calipers. Physics 9-11 Unit 1, Physical Quantities and Measurement. Zero error is positive as zero line of vernier scale is on the right side of the zero of the main scale. Example 1.1. Find the diameter of a cylinder placed between the outer jaws of vernier calipers as shown in figure 1.8. Solution. Zero correction on closing the jaws of vernier calipers, the position of vernier scale as shown in figure 1.7, b. Main scale reading equals 0 cm. Vernier division coinciding with main scale equals 7 division. Vernier scale reading is equal to 7 by 0.01 cm equals 0.07 cm. Zero error equals 0.0 cm plus 0.07 cm equals plus 0.07 cm. Zero correction, Z.C, equals 0.07 cm. Diameter of the cylinder. Main scale reading equals 2.2 cm. When the given cylinder is kept between the jaws of the vernier calipers as shown in figure 1.8. Vernier division coinciding with main scale division equals 6 division. Vernier scale reading is equal to 6 by 0.01 cm equals 0.06 cm. Observed diameter of the cylinder equals 2.2 cm plus 0.06 cm equals 2.26 cm. Correct diameter of the cylinder equals 2.26 cm. 0.07 cm equals 2.19 cm. Thus, the correct diameter of the given cylinder as found by vernier calipers is 2.19 cm. Quick quiz 1. What is the least count of the vernier calipers? 2. What is the range of the vernier calipers used in your physics laboratory? 3. How many divisions are there on its vernier scale? 4. Why do we use zero correction? Digital vernier calipers. Digital vernier calipers has greater precision than MECHANICALVER calipers. Least count of digital vernier calipers is 0.01 mm. Physics 912 Unit 1, Physical Quantities and Measurement. Spindle. Main scale. Circular scale. Ratchet. Metal frame. Lock. Hollow cylinder or sleeve thimble. Stud. 0, 5, 80, 75, 70, 65. Index line. 60. Relative sizes of cells and their components. Small molecule. Virus. Bacterium. Animal cell. Cell plant. Electron microscope. Light microscope. Nanotechnology. 1A. 1 nanometer. 10 nanometers. 100 nanometers. 1M. 10M. 100M. 1 millimeter. 1. Tidbits. Relative sizes of molecules and microorganisms. Screw gauge. A screw gauge is an instrument that is used to measure small lengths with accuracy greater than a vernier caliper. It is also called as micrometer screw gauge. A simple screw gauge consists of a U-shaped metal frame with at its one end as shown in figure 1.9. A hollow cylinder, or sleeve, has a millimeter scale over it along a line called index line parallel to its axis. The hollow cylinder acts as a nut. It is fixed at the end of U-shaped frame opposite to the stud. A thimble has a threaded spindle inside it. As the thimble completes one rotation, the spindle moves 1 millimeter along the index line. It is because the distance between consecutive threads on the spindle is 1 millimeter. This distance is called the pitch of screw on the spindle. The thimble has 100 divisions around its one end. It is the circular scale of the screw gauge. As thimble completes one rotation, 100 divisions pass the index line, and the thimble moves 1 millimeter along the main scale. Thus, each division of circular scale crossing the index line Moves the thimble through 100 mm or 0.01 mm on the main scale. Least count of a screw gauge can also be found as given below. Figure 1.9, a micrometer screw gauge. Physics 913 Unit 1, Physical Quantities and Measurement. 0. 5. 0 95 90 85. 0 error is negative if 0 of circular scale has passed 0 of main scale. Here 0 error is minus 0.05 mm as 5 divisions of circular scale has crossed the index line. 0. 10. 509. 590. As 0 of circular scale is exactly on the index line, hence there is no 0 error. 0. 30 25. 20. 15. 10. 0 error is positive if 0 of circular scale has not reached 0 of main scale. Here 0 error is plus 0.18 mm as 18th division on circular scale is before the index line. 5 equals 0.01 mm equals 0.001 centimeters. Thus least count of the screw gauge is 0.01 mm or 0.001 centimeters. Working of a screw gauge. The first step is to find the 0 error of the screw gauge. 0 error. To find the 0 error, close the gap between the spindle and the stud of the screw gauge by rotating the ratchet in the clockwise direction. If 0 of circular scale coincides with the index line, then the 0 error will be 0 as shown in figure 1.10a. 0 error will be positive if 0 of circular scale is behind the index line. In this case, multiply the number of divisions of the circular scale that has not crossed the index line with the least count of screw gauge to find 0 error as shown in figure 1.10b. 0 error will be negative if 0 of circular scale has crossed the index line. In this case, multiply the number of divisions of the circular scale that has crossed the index line with the least count of screw gauge to find the negative 0 error as shown in figure 1.10c. Example 1.2. Find the diameter of a wire using a screw gauge. Solution. The diameter of a given wire can be found as follows. I. Close the gap between the spindle and the stud of the screw gauge by turning the ratchet in the clockwise direction. 2. Note main scale as well as circular scale readings to find 0 error and hence 0 correction of the screw gauge. Figure 1.10, 0 error in a screw gauge, A, 0, B, plus 0.18 mm, C, minus 0.05 mm. C. B. A. Physics 914 Unit 1, Physical Quantities and Measurement. Wire placed between the gap. 0 95 90 85 80 75. Circular scale reading is 85 division. Multiply it by 0.01 millimeters. This is equal to 0.85 millimeters. Main scale reading, leaving the fractional part, is 1 millimeter. 0. Here main scale reading is 0 millimeters and 23rd division of circular scale is before the index line. Hence 0 error is 0 plus 24 times 0.01 millimeter equals 0.24 millimeters. 35. 30. 25. 20. 15 10. 3. Open the gap between stud and spindle of the screw gauge by turning the ratchet in anti-clockwise direction. Place the given wire in the gap as shown in figure 1.11. Turn the ratchet so that the object is Press gently between the studs and the spindle. 4. Note main scale as well as circular scale. Readings to find the diameter of the given wire. V. Apply zero correction to get the correct diameter of the wire. 6. Repeat steps 3, 4, and V at different places of the wire to obtain its average diameter. Zero correction closing the gap of the screw gauge, figure 1.12. Main scale reading equals 0 mm. Millimeter circular scale reading is equal to 24 times 0.010. Error of the screw gauge equals 0 mm plus 0.24 mm. Equals plus 0.24 mm. Zero correction ZC equals minus 0.24 mm. Diameter of the wire, figure 1.11. Main scale reading equals 1 mm. When the given wire is pressed by the stud and spindle of the screw gauge. Mini exercise. 1. What is the least count of a screw gauge? 2. What is the pitch of your laboratory screw gauge? 3. What is the range of your laboratory screw gauge? 4. Which one of the two instruments is more precise and why? Useful information. Least count of ruler is 1 millimeter. It is 0.1 millimeters for vernier calipers and 0.01 millimeters for micrometer screw gauge. Thus measurements taken by micrometer screw gauge are the most precise than the other two. Physics 9:15 Unit 1, Physical Quantities and Measurement. Figure 1.11, Measuring the diameter of a wire using micrometer screen gauge. 0510-105. Stirrup beam balancing screw. Hook. Plumb line. Pen pointer. Scale. Pillar. Arrestment knob leveling screw. Pointer is at 0. Beam is balanced. No divisions on circular scale equals 85 division. Circular scale reading is equal to 85 by 0.01 mm equals 0.85 mm. Observed diameter of the given wire equals 1 mm plus 0.85 mm equals 1.85 mm. Correct diameter of the given wire equals 1.85 mm to 0.24 mm equals 1.61 mm. Thus diameter of the given wire is 1.61 mm. Mass measuring instruments. Pots were used to measure grain in various parts of the world in the ancient times. However, balances were also in use by Greeks and Romans. Beam balances such as shown in figure 1.13 are still in use at many places. In a beam balance, the unknown mass is placed in one pan. It is balanced by putting known masses in the other pan. Today people use many types of mechanical and electronic balances. You might have seen electronic balances in sweet and grocery shops. These are more precise than beam balances and are easy to handle. Physical balance. A physical balance is used in the laboratory to measure the mass of various objects by comparison. It consists of a beam resting at the center on a fulcrum. Mini exercise 1. What is the function of balancing screws in a physical balance? 2. On what pan we place the object and why? Figure 1.14, a physical balance. Physics 9:16 Unit 1, Physical Quantities and Measurement. 0. As shown in the figure 1.14. The beam carries scale pans over the hooks on either side. Unknown mass is placed on the left pan. Find some suitable standard masses that cause the pointer to remain at 0 on raising the beam. As shown in the figure 1.14. The beam carries scale pans over the hooks on either side. Unknown mass is placed on the left pan. Find some suitable standard masses that cause the pointer to remain at 0 on raising the beam. Example 1.3. Find the mass of a small stone by a physical balance. Solution: follow the steps to measure the mass of a given object. I. Adjusting the leveling screws with the help of plumb line to level the platform of physical balance. 2. Raise the beam gently by turning the arresting knob clockwise. Using balancing screws at the ends of its beam, bring the pointer at 0 position. 3. Turn the arresting knob to bring the beam back on its supports. Place the given object, stone, on its left pan. 4. Place suitable standard masses from the weight box on the right pan. Raise the beam. Lower the beam if its pointer is not at 0. V. Repeat adding or removing suitable standard masses in the right pan till the pointer rests at 0 on raising the beam. 6. Note the standard masses on the right pan. Their sum is the mass of the object on the left pan. Lever balance. A lever balance such as shown in figure 1.15 consists of a system of levers. When lever is lifted placing the object in one pan and standard masses on the other pan, the pointer of the lever system moves. The pointer is brought to 0 by varying standard masses. Figure 1.15, a lever balance. Laboratory safety equipment. Fire extinguisher. Physics 917 Unit 1, Physical Quantities and Measurement. Electronic balance. Electronic balances such as shown in figure 1.16 come in various ranges: milligram ranges, gram ranges, and kilogram ranges. Before measuring the mass of a body, it is switched on and its reading is set to 0. Next, place the object to be weighed. The reading on the balance gives you the mass of the body placed over it. The most accurate balance. The mass of 1 rupee coin is done using different balances as given below. A. Beam balance. Let the balance measures coin's mass equals 3.2 g. A sensitive beam balance may be able to detect a change as small as of 0.1 g or 100 milligrams. B. Physical balance. Let the balance measures coin's mass equals 3.24 g. Least count of the physical balance may be as small as 0.01 g or 10 milligrams. Therefore, its measurement would be more precise than a sensitive beam balance. C. Electronic balance. Let the balance measures coin's mass equals 3.247 g. Least count of an electronic balance is 0.001 g or 1 milligram. Therefore, its measurement would be more precise than a sensitive physical balance. Thus, electronic balance is the most sensitive balance in the above balances. Stopwatch. A stopwatch is used to measure the time interval of an event. There are two types of stopwatches: mechanical and digital, as shown in figure 1.17 and 1.18. A mechanical stopwatch can measure a time interval up to a minimum 0.1 second. Digital stopwatches commonly used in laboratories can measure a time interval as small as 1/100 second or 0.01 second. Pan, glass case, screw. 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 29, 31, 28, 27, 26, 25, 24, 23, 22, 21, 20, 19, 18, 17, 16, 15, 58, 59, 60, 57, 56, 55, 54, 53, 52, 51, 50, 49, 48, 47, 46, 45, 44, 43, 42, 41, 40, 39, 38, 37, 36, 35, 34, 33, 32, 31, 1, 2, 3, 4, 5, 6, 8, 7, 9, 10, 11, 12, 13, 14, 15. Useful information. The precision of a balance in measuring mass of an object is different for different balances. A sensitive balance cannot measure large masses. Similarly, a balance that measures large masses cannot be sensitive. Some digital balances MEASUREEVENSMALLER difference of the order of 0.0001 G or 0.1 milligrams. Such balances are considered the most precise balance. Figure 1.16, an electronic balance. Figure 1.17, a mechanical stopwatch. Physics 918 Unit 1, Physical Quantities and Measurement. 200 milliliters, 180, 160, 140, 120, 180, 60, 40, 20, 0. 200 milliliters, 180, 160, 140, 120, 180, 60, 40, 20, 0. A. Incorrect position. A. Correct position. Figure 1.18, a digital stopwatch. Laboratory safety. Equipments. A school laboratory must have safety equipment such as waste disposal basket, fire extinguisher, fire alarm, first aid box, sand and water buckets, fire blanket to put off fire. Substances and equipment that need extra care must bear proper warning. Signs such as given below. How to use a stopwatch. A mechanical stopwatch has a knob that is used to wind the spring that powers the watch. It can also be used as a start, stop and reset button. The watch starts when the knob is pressed once. When pressed second time, it stops the watch, while the third press brings the needle back to zero position. The digital stopwatch starts to indicate the time lapsed as the start-stop button is pressed. As soon as start-stop button is pressed again, it stops and indicates the time interval recorded by it between start and stop of an event. A reset button restores its initial zero setting. Measuring cylinder. A measuring cylinder is a glass or transparent plastic cylinder. It has a scale along its length that indicates the volume in milliliter, ml, as shown in figure 1.19. Measuring cylinders have different capacities. From 100 milliliters to 2,500 milliliters. They are used to measure the volume of a liquid or powdered substance. It is also used to find the volume of an irregular-shaped solid, insoluble in a liquid by displacement method. The solid is lowered into a measuring cylinder containing water liquid. The level of water liquid rises. The increase in the volume of water liquid is the volume of the given solid object. Figure 1.19. A. Wrong way to note the liquid level, keeping I above liquid level. B. Correct position of I to note the liquid level, keeping I at liquid level. Physics 919 Unit 1, Physical Quantities and Measurement. How to use a measuring cylinder. While using a measuring cylinder, it must be kept vertical on a plane surface. Take a measuring cylinder. Place it vertically on the table. Pour some water into it. Note that the surface of water is curved as shown in Figure 1.19. The meniscus of the most liquids curve downwards while the meniscus of mercury curves upwards. The correct method to note the level of a liquid in the cylinder is to keep the eye at the same level as the meniscus of the liquid as shown in Figure 1.19b. It is incorrect to note the liquid level keeping the eye above the level of liquid as shown in Figure 1.19a. When the eye is above the liquid level, the meniscus appears higher on the scale. Similarly, when the eye is below the liquid level, the meniscus appears lower than actual height of the liquid. Measuring volume of an irregular shaped solid. Measuring cylinder can be used to find the volume of a small irregular shaped solid that sinks in water. Let us find the volume of a small stone. Take some water in a graduated measuring cylinder. Note the volume 6 of water in the cylinder. Tie the solid with a thread. Lower the solid into the cylinder till it is fully immersed in water. Note the volume Vf of water and the solid. Volume of the solid will be Vfi. 1.7 Significant figures. The value of a physical quantity is expressed by a number followed by some suitable unit. Every measurement of a quantity is an attempt to find its true value. The accuracy in measuring a physical quantity depends upon various factors, plus the quality of the measuring instrument, plus the skill of the observer, plus the number of observations made. For example, a student measures the length of a book as 18 centimeters using a measuring tape. The numbers of significant figures in his/her measured. Laboratory safety rules: the students should know what to do in case of an accident. The charts or posters are to be displayed in the laboratory to handle situations arising from any mishap or accident. For your own safety and for the safety of others in the laboratory, follow safety rules given below. Do not carry out any experiment without the permission of your teacher. Do not eat, drink, play, or run in the laboratory. Read the instructions carefully to familiarize yourself with the possible hazards before handling equipments and materials. Handle equipments and materials with care. Do not hesitate to consult your teacher in case of any doubt. Do not tamper with the electrical appliances and other fittings in the laboratory. Report any accident or injuries immediately to your teacher. Physics 920 Unit 1, Physical Quantities and Measurement. Rules to find the significant digits in a measurement. Digits other than 0 are always significant. 27 has 2 significant digits. 275 has 3 significant digits. 2 zeros between significant digits are also significant. 2705 has 4 significant digits. 3 final 0 or zeros after decimal are significant. 275.00 has 5 significant digits. 4 zeros used for spacing the decimal point are not significant. Here zeros are placeholders only. 0.03 has 1 significant digit. 0.027 has 2 significant digits. Example. Value R2. The left digit 1 is the accurately known digit, while the digit 8 is the doubtful digit for which the student may not be sure. Another student measures the same book using a ruler and claims its length to be 18.4 centimeters. In this case, all the 3 figures are significant. The 2 left digits 1 and 8 are accurately known digits. Next digit 4 is the doubtful digit for which the student may not be sure. A third student records the length of the book as 18.425 centimeters. Interestingly, the measurement is made using the same ruler. The numbers of significant figures is again 3, consisting of 2 accurately known digits 1, 8 and the first doubtful digit 4. The digits 2 and 5 are not significant. It is because the reading of these last digits cannot be justified using a ruler. Measurement up to third or even second decimal place is beyond the limit of the measuring instrument. An improvement in the quality of measurement by using better instrument increases the significant figures in the measured result. The significant figures are all the digits that are known accurately and the one estimated digit. More significant figure means greater precision. The following rules are helpful in identifying significant figure. I. Non-zero digits are always significant. 2. Zeros between two significant figures are also significant. 3. Final or ending zeros on the right in decimal fraction are significant. 4. Zeros written on the left side of the decimal point for the purpose of spacing the decimal point are not significant. V. In whole numbers that end in one or more zeros without a decimal point. These zeros may or may not be significant. In such cases, it is not clear which zeros serve to. Physics 921 Unit 1, Physical Quantities and Measurement. 22. Locate the position value and which are actually parts of the measurement. In such a case, express the quantity using scientific notation to find the significant zero. Example 1.4. Find the number of significant figures in each of the following values. Also express them in scientific notations. A. 100.8 sb, 0.00580 kilometers. C. 210.0 g. Solution. A. All the four digits are significant. The zeros between the two significant figures 1 and 8 are significant. To write the quantity in scientific notation, we move the decimal point 2 places to the left, thus 2 100.8 s is equal to 1.008 times 10 s. B. The first two zeros are not significant. They are used to space the decimal point. The digit 5, 8 and the final zero are significant. Thus there are three significant figures. In scientific notation, it can be -3 written as 5.80 by 10 kilometers. C. The final zero is significant since it comes after the decimal point. The zero between last zero and 1 is also significant because it comes between the significant figures. Thus the number of significant figures in this case is 4. In scientific notation, it can be written as 210.0 g is equal to 2.100 times 10 g. Rounding the numbers. If the last digit is less than 5, then it is simply dropped. This decreases the number of significant digits in the figure. For example, 1.943 is rounded to 1.943 significant figure. 2. If the last digit is greater than 5, then the digit on its left is increased by 1. This also decreases the number of significant digits in the figure. For example, 1.47 is rounded to two significant digits 1.5. 3. If the last digit is 5, then it is rounded to get nearest even number. For example, 1.35 is rounded to 1.4 and 1.45 is also rounded to 1.4. Physics 9 Unit 1, Physical Quantities and Measurement. 23. Summary. Physics is a branch of science that deals with matter, energy, and their relationship. Some main branches of physics are mechanics, heat, sound, light, optics, electricity and magnetism, nuclear physics and quantum physics. Physics plays an important role in our daily life. For example, electricity is widely used everywhere. Domestic appliances, office equipment, machines used in industry, means of transport and communication etc. work on the basic laws and principles of physics. A measurable quantity is called a physical quantity. Base quantities are defined independently. 7 quantities are selected as base quantities. These are length, time, mass, electric current, temperature, intensity of light and the amount of a substance. The quantities which are expressed in terms of base quantities are called derived quantities. For example, speed, area, density, force, pressure, energy, etc. A WORLD, WIDESYSTEMOF measurements is known as International System of Units, SI. In SI, the units of 7 base quantities are meter, kilogram, second, ampere, Kelvin, candela and mole. The words or letters added before a unit and stand for the multiples or submultiples of that unit are known as prefixes. For example, kilo, mega, milli, micro, etc. A way to express a given number as a number between 1 and 10 multiplied by 10 having an appropriate power is called scientific notation or standard form. An instrument used to measure small lengths such as internal or external diameter or length of a cylinder, etc. is called as vernier calipers. A screw gauge is used to measure small lengths such as diameter of a wire, thickness of a metal sheet, etc. Physical balance is a modified type of beam balance used to measure small masses by comparison with greater accuracy. A stopwatch is used to measure the time interval of an event. Mechanical stopwatches have least count up to 0.1 seconds. Digital stopwatch of least count 0.01 s are common. A measuring cylinder is a graduated glass cylinder marked in milliliters. It is used to measure the volume of a liquid and also to find the volume of an irregular-shaped solid object. All the accurately known digits and the first doubtful digit in an expression are called significant figures. It reflects the precision of a measured value of a physical quantity. Physics 9 Unit 1, Physical Quantities and Measurement. Encircle the correct answer from the given choices. The number of base units in SI